Oh, good evening, everyone. I want to thank you for coming. I know it's really, really cold out, so thank you for braving it. Um, I'm pretty excited with tonight's talk. We're joined by Brendan Schenk. He's the Senior Principal Engineer with Marvell Custom Compute and Storage. And he's going to be talking to us about AI-driven advanced packaging. So please give Brandon a big round of applause.
Thank you. So yes, custom compute and storage until last Friday. So like typical engineering reorgs. So I don't know what my new title is yet, but I'm still a senior principal engineer. That's good news. I started my career at IBM. I know some of you from there as a clock logic and a physical designer. Stayed with IBM until the microelectronics divestiture to Global Foundries in 2015. So IBM sold all of its fabs off to Global Foundries, who had really was created out of AMD. AMD going fabless, Chartered Semiconductor, who was around in the early 2000s, and really started to kind of focus on our continued custom ASIC business until Global Foundries decided to start investing more heavily into differentiated technology rather than leading node technology, which made a lot of what we did difficult, right? As we were going after big data, hyperscaler type customers, Global Foundries was moving more towards higher volume, less cutting edge technology, or at least less leading node technology, I should say. They are still very cutting edge. So we divested yet again to a fabless company called Verasemi. We were eventually picked up by Marvell Semiconductor. And shameless plug, I will do my best to not sound like a Marvell marketer. This is an industry presentation. But shameless plug, Marvell is a very different company than it was maybe even 5 or 10 years ago, if some of you are familiar with who they are. It's been a radical transformation, focus on real cutting edge, like I said, hyperscaler, big data, infrastructure stuff. And that's kind of what I do today. So I'm really in the same job I've been in for 20 years, even though I've been moved. I really haven't moved myself. Most of my focus today is on leading design teams, sometimes as a project manager, largely as a technical lead for some of the industry leading companies in hyperscale, big data, analytics, Microsoft, Google, Meta, networking, Cisco, NVIDIA. We've done some work with them. And that's really kind of what I do. My style of presentation is kind of interactive. Like if you've got questions, feel free to interrupt me. If you'd rather wait till the end, that's okay too, but I am perfectly fine with interruptions. So if you've got them, just let me know. So this is a little bit about AI and a lot about how it's disrupting silicon and package engineering. But maybe to kind of start, right, for those who, I know everybody's from sort of different backgrounds, but the human brain is really made up of about 100 billion neurons, right? And they're organized in a way that when a neuron fires, it sends signals to other neurons and they can start reacting. And as they react in volume, thought is formed. And we can model this mathematically with equations, right? And these are just multiplier accumulator units. This is pretty basic math. For a given activation function, you have a set of signals and a set of weights. And you can weight each of those signals differently as you learn, as you train your machine to model effectively an artificial neuron. And you can join and collect all of those artificial neurons into a neural network. You have a whole set of inputs with their weights and their functions leading to a set of outputs. And they go through one or two or even several intermediate layers called hidden layers here. But the more layers you have, generally 2+, we call that deep learning or a deep neural network. But effectively, a set of inputs generates a set of outputs. I'll just pause. I mean, has everybody used something like ChatGPT or Copilot or Google search or Bing search. Those are certainly generative AI, but certainly if you've interacted directly with Copilot, directly with ChatGPT, you've kind of seen the power of inference. A simple example, very simple example, couple of parameters, simple. I've got some inputs that I want to feed into a training machine. I've got starfish, which have a star shape and a ring pattern. And I've got some sea urchins, which have an oval pattern or an oval shape and a striped pattern. And I've established a set of 4 parameters: shapes, star and oval, and patterns, ring and striped. And to make it interesting, I've thrown in kind of an oddball. I've got a ring patterned sea urchin there. And I've created my weighted averages, and you can see there's some pretty strong, my pointer works great. There's some pretty strong linkages here with one weak linkage from my sea urchin. This is how I've trained my design. And now when I run inference, this is actually when I'm running it, when I'm interacting with it, I'm asking it to tell me what I've put in. So my starfish, right, links to his star shape, links to his ring pattern, and says, yep, you've got a starfish. Then I throw another one in. I throw, hey, how about a seashell? Something I haven't really trained for, but generative AI, do your best shot. It links to the oval shape, but it doesn't really have a pattern or anything else to go by. And it gives me its best guess, you've got a sea urchin. And I'm sure everybody's experienced something like this with generative AI, where it's almost there, but not quite. But over time, and with many, 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 many more parameters, this inference starts to get really good. Large language models are specific applications of artificial networks. We can actually start generating languages. These have existed for years. You can see many here that some might be familiar with. Certainly GPT, currently in version 4. There's GLAM from Google. There's Copilot from Microsoft. These have only really become interesting in the last few years because the number of parameters going into the training algorithms rival the number of neurons in the human brain and actually exceed and are starting to become as smart as a person. That could have generated a laugh, but yes. Let's talk about the computational needs of some of these AI these AI trainers. So GPT, right? Arguably the most famous of the generative AI clients. ChatGPT 4 is projected or estimated to use roughly 2 trillion parameters. That's debatable. There's a lot of different architectural changes they've made, but if it scales from GPT 3, 2 trillion parameters, it takes 10 to the 16th, 10 to the power of 16 floating point operations for this thing to run inference. That's an amazing amount of compute power. That's 10 petaflops. Training, however, is where the money is. Training is where these things really consume their computational power. 10 to the 25th flops for training. That is
a lot.
Yada flops, I think. I don't even use Yada on a daily basis. I don't even know how that works, but 10 Yada flops, I think, to train. If we take the newest high performance commercially available GPU available today, an NVIDIA H100, and we train GPT-4 with that single GPU, it has capable of 989 teraflops with 80 gigabytes, pardon me, of onboard memory. The training time would take 115,740 days, or 317 years. Now, that's clearly not acceptable. We need training to be minutes or hours. Even if we wanted this to be days, 30 days to train, I would need 3,858 of these GPUs. And if you go online and look today, the cost of a single NVIDIA H100 system is about $30,000. So to train GPT-4 in 30 days would be an investment of upwards of $115 million. And that's not to count all of the external memory, all of the input and output, and all of the power consumption that this is going to use. So how do we scale hardware to meet these demands? Well, for some who are familiar with hardware design, chip design specifically, Moore's law, digital scaling is slowing down. I mean, Moore's law is almost dead. It's certainly not meeting the targets that we have expected over the years. Reticle size of die and chip design limits die growth. Analog doesn't scale at all, like anymore. We're pretty much stuck with analog. Power and thermal is more difficult to control. And there's clearly more compute power, more flops needed to achieve the performance necessary per chip, and significantly more memory. I pulled this graph off the web just the other day, and it shows the projected exponential spend in AI as an industry compared to the Higgs boson search, the Apollo mission projects of the 70s, and then the total US GDP. And what I thought was interesting is that this already assumes a compute per dollar doubling every 4 years, which is already almost 2x what Moore's law would suggest it would be. Granted, this is based on cost and not necessarily size or scale, but generally we expect cost to track with Moore's law. What about memory scaling? So if you look over the last 100 years at commercial airspeed, it was steadily increasing until about the 1970s, when we hit that fundamental limit. You just can't really go any faster. SRAM densities have really done the same thing in time. Now, granted, they've done it a lot faster. SRAM densities were increasing about 10x faster than commercial airspeed, but they really hit the same limitation. We're just not scaling anymore. And the problem with not being able to scale is that we need more silicon area to make up for the needed performance gains at every node. In 7 nanometer, if we had a reticle size chip, 700-ish square millimeters, we would hit our performance targets. In the next node, we would expect a doubling of performance. But to do that, I would need significantly more chip area. In 5 nanometers, 60% more chip area. We move to 3 nanometer, and my silicon area increases again, 1900 square millimeters, to the point where now I'm in 2 nanometer, and I'm almost doubling from what I had in 3 nanometer. This is 4 reticle size die, almost 5 reticle size die, just to meet the linear performance targets that I would expect to see node over node. What about power? Right. So some may remember the bipolar days before the 90s. CMOS came around, revolutionized power density. But we quickly hit a limit with CMOS. I mean, those curves almost track perfectly. Within 10 years, CMOS was at its limits. And we really had no way to go forward with power scaling. Clicker. There we go. So much so that CPU companies, especially Intel, where Pat Gelsinger is credited with this chart, predicted that the only way to scale would be through clock frequency. I think everybody remembers when you bought the newest Intel processor, or processor in general, this isn't about Intel, that really all you looked for was a clock frequency improvement. 2 gigahertz, 2.5 gigahertz, 3 gigahertz, 4 gigahertz, to the point where they started to see almost logarithmic growth in the projected power as these CPUs scaled. The sky is going to fall. Or is it? So when we actually look back, we see that CPU power levels really stayed level, even when people projected surface of the sun temperatures. The performance gains per generation just became less dramatic. We just didn't scale anymore. And we could add more processors when area and power scaling allowed it. This was the advent of the super system, right? The massive scalar systems. But it might be starting. The sky falling, that is. GPU and machine learning powers are actually outpacing those CPU competitors. Nobody's talking about CPUs anymore. We don't use CPUs for generative AI. These are specialized processors, often called GPUs, but really a unique type of breed. And the limited silicon area scaling results in these higher performance targets. And really the only way to hit them is to bump voltage. And we're seeing this a lot in our hyperscalers, where we're not doing things at steady voltages. We're not lowering voltage at every node. We're actually raising voltage as we get into these lower nodes just to keep hitting performance. And that is a direct impact on power density and thermal concerns. Oh, forgot my little animation there. So with all of this extra silicon comes bigger packages. And you can see real die pictures of some of the things we've done in the near past with projections on what things will look like next. So the new airspeed limit to us is a stupid tray. And if you're not familiar, these are the JEDEC trays that chips are shipped in. JEDEC is a standard like IEEE, and they have fixed sizes, and we're no longer fitting even in these trays. And so our solution and the solution of the industry is clearly innovation, right? So we're starting to see things like 3.5D integration, which gives us more silicon area in the same footprint. We're starting to see custom HBM and DRAM and LPDDR stacks. Instead of just buy these from vendors, we're actually partnering with vendors. Industry is partnering with vendors to create custom solutions at every step of the way. Memory design is becoming very bespoke rather than compilers that memory vendors or memory designers are putting together. We're customizing them at every stage at the transistor level to allow us to hit the density and performance necessary that we're not getting through technology scaling. We're also creating unique optics systems for lower power and beachfront access, which are allowing for a lot of these massive systems. Clearly, more silicon in a system. Even if you can stack it in footprint, you need connectivity, lots and lots of massive I/O. And backside power delivery. So this is where we're actually providing power through the backside of the silicon die, giving us yet another dimension with which to open up area in the die itself for logic. That allows us to continue to scale density, but also reduce IR drop and control some of the voltage losses that we would otherwise have. So the other thing we're doing is we're targeting the very high performance nodes, the very newest nodes, 2 nanometer, 18A from Intel, 1.4 nanometer from TSMC, to the critical logic function, the stuff that really needs to run fast, the stuff that really needs the lowest or the highest density and the lowest lithography to function. We're jettisoning I/O and analog function to more efficient nodes. They're not scaling. Let's leave them in the nodes that make sense and worry about how to attach them through packaging. I mentioned we're consolidating memory solutions, working with memory vendors to create custom solutions in that space. We're creating complex IP for interconnect. So, unique SerDes, things like extreme short reach SerDes, ultra high density interconnect, die to die interfaces. And we're leveraging the latest in silicon package design capabilities, 2.5D stacking, 3D stacking, 3.5D stacking. Today I read a report that interposer on interposer is something that's now being looked at. And then I mentioned backside power and optical. And by the way, if there's questions, I don't know how many people are chip designers, but if there's questions about some of this, please ask. All right, so what does that mean for accelerating our package technology? So this will maybe help get some people involved here. And which one is which? And you may need to be a chip designer to understand this, but maybe not. A logic wafer is kind of a traditional wafer. This is where we reticle the chips and we build them. An interposer wafer, make sure I go in order. An interposer wafer is the larger piece of silicon that sits between the chip you want to build and the package that it's going to go on. It allows for extra interconnect between multiple chips stacked on top of it. And 3D is true 3D. Any guesses? Okay, we'll just give away the answer. So this is kind of what they look like. And this is a simple interposer. I think the 3D one's cool. That's a little bit of color effect, but actually because they're 3D stacked, you actually get quite a bit of topology variation. They're pretty sweet to look at. But sorting things out a little bit. There's a couple technologies that have come and are now starting to actually fade as far as scaling goes. FinFET, this was huge about 8 years ago, 7 years ago. The gate all around, if you will. Oh, that's hard to see. Those are 2 buckets, by the way. FinFET, is that a chip technology or is that a package technology?
Package.
Oh, okay, good. So this'll out the people who aren't chip designers, so that's good. Yeah, this is a chip technology. How about flip chip BGA? Better hit the clicker. Flip chip BGA was like 2000s, right? This was a unique way to package. You flip the chip over. I just said the word. Package. Backside power delivery.
Chip.
Good answer. Chip. Interposers.
Chip.
Yeah, you're kind of both right. I'm going to put it next to the package bucket, but it's built like a chip, but it's made for packaging. How about 3D? This is where we actually stack silicon on top of a package.
Chip.
Chip-ish?
Package-ish.
Yeah, ish. 3D, 3.5D integration. So this is a 3D stack on top of an interposer on top of a package.
More on the package side.
I got lost too. That's kind of right in between. Yep. Wafer scale integration. Has anybody seen wafer scale integration or knows what wafer scale integration is? It's amazing. These are full. I should have brought my wafer. I have a wafer at work. Full 300. I don't have one of these, but I have just a wafer. I have a lot of them. 300 millimeter wafer that doesn't get diced. It's actually built to have, and I'll talk about this. It's actually built to have connectivity at the wafer level itself through custom RDL or some other technology to allow this thing to function as a complete system. And this is Cerebras, by the way. I'll show you a bigger picture of it in a second. Is that wafer? Is that chip or package?
Both.
Yeah, I don't know either. The point is these buckets don't fit anymore. We don't have chip anymore, and we don't have package anymore. We have something in between. And this is a joke because I stole the slide. But the new normal is that the system, how it's used collectively at the macroscopic level, is how design is starting to be done.
Hey, Brandon, quick question.
Yeah, please.
2.5D in your definition, is that just MCM, basically multiple chips?
2.5D, yeah, 2.5D is actually interposer. So
Okay.
2.5D, and it comes into the way that the interconnect is done. And I'll show you a picture in a second, but it's when you move from traditional bumps,
Yep.
sometimes called C4s in IBM terminology or other terminologies, to micro bumps.
Okay.
The JEDEC trays, as I said earlier, are getting too small. Reticle size is unchanged. That is a limit of lithography. But the package size isn't. You can see it's starting to spike there as Moore's law died. I'll go on the record, died, and package started to take over. But what's interesting is you look out just a couple of years, and the recent trend in package size is exploding, just exploding. And that's, if you go back a few slides and you saw my question marks on the next big package, this is why. We are still learning what those look like. What industry is seeing right now, new engagement, is multiple reticle size die. So these are 760-ish square millimeters each. And this is all my logic function. This is my 2 nanometer, my 1.8, my 1.4 nanometer logic, my highest performance logic, condensed onto 4 reticle size die. And they may be the same and they may not be. To get all the I/O to work, I need a bunch of I/O chiplets. So I'm putting my analog and my SerDes out on these chiplets, and I'm connecting them to those main die through custom interfaces. I need boatloads of memory, like HBM, DRAM, stacks, whatever I can do to get it close. And all of this has to live on the same thing. A CoWoS interposer, something like that. Yeah.
So can you talk about how much I/O between those on that package?
I can. In fact, I have a slide on it. Yeah. Thank you. That helps. This thing is so big that we're getting 4 of them on a wafer. That's how big the interposer becomes. And that's enormous. It's so enormous that the packaging is now the bulk of the expense for most of these chip designs. Go back 5 years, maybe, and 30% of your cost was package and test. 70% was your silicon cost. And that is totally flipped in the last 5 years. We're now seeing about 30% in silicon cost and the rest of it in integration at the package level. So, will this trend of increasing integration slow down? You can tell there's a little bit of a marketing bent to these. I apologize. I stole the slides to some extent. No, absolutely not. In fact, this is a slide from TSMC. You can see just the evolution of CoWoS and the projected and where it's projecting to go. We started with CoWoS with about 3.3 reticle size. This is the size of the interposer for the reticle, so we can snap up to 3.3 reticle size in an interposer. And that quickly moved to CoWoS, the next generation of CoWoS, which allowed for 5.5, which gives you room for 12 HBM and about just greater than 2x your compute power. The latest generations of CoWoS are looking to be about 9 reticle size, which is enormous again. Similar HBM count, but now I can get a much larger substrate and tremendously more compute power because I haven't really hit that equilibrium with memory bandwidth yet. And all of these are sort of starting to project a system on wafer concept, like the Cerebras picture you saw up top, where I can build 43 reticle size without any substrate, literally a system on a wafer. Yeah, here's the picture. So this is the Cerebras. I think it's WSE3. This is a 5 nanometer technology. The reason it's not in 3 or 2 is because yield matters, and getting a perfect wafer out of newer technologies is very difficult. Even out of 5 nanometer is difficult. And then Tesla Dojo. This is their inference used internally for training self-driving. Integrated fan-out wafer. I think this one was 7 nanometer, full system on wafer.
And you need a perfect wafer out of that. You can't have any.
Well, yes. So yeah, you caught me on that. You build in for defects, so partial good strategies, redundant logic, things like that. But you still want to drive up your yield as high as you possibly can for maximum performance.
What kind of yield are they getting? Even with all the redundancy?
I'm no longer part of a fab, so I don't know.
No.
I think we can.
I probably wouldn't say.
Yeah, well, I don't know because I don't work for these companies. But with partial good strategies, with redundant logic strategies, the goal would be as close to 100%. Now, in actuality, that's not what you're going to get. We would see. I personally have not done wafer scale integration projects yet. But for some of our more classic chip designs, we can test upwards of 80 to 90% good yield. Our goal is always 100, but there are manufacturing defects that you just can't always protect against. All right, so yeah.
That's 80, 90% of the wafers or the chips on a wafer. This is a whole wafer.
This is a whole wafer. Right. So if I've got one area that's dead, so maybe I've built this so that this whole thing is redundant. Maybe that's just a spare core, or maybe there's pieces of it that are spare. Right. It depends on what the spare strategy is. Right. That's a logic design and an architecture question. But you would want to build these so that you can, you're not building 1,000 of these to get one good. So you would have to over design to achieve your performance.
So how much does design for redundancy, design for test, all that impact the amount of
a tremendous amount. That's literally that shift. So I mentioned the 70-30 split. That's for, I'll call it traditional packaging. When you get to this kind of scale, I think it's 1090. right? I think that they probably spent 90% of their time building in for test defects and only 10% of their time into and cost into actual design. Assuming that a lot of that design time is based on what I'm doing for test. Test and package were an afterthought, right? It was chip first, then package and test sort of ran parallel. And now you don't start chip design until you know how you're going to work around some of those defect issues. And so it permeates the design cycle much more to the point where it's skewing that balance in cost. Other questions? Thank you for those. So it was, who asked about the interconnect? Was that you, Chris? Yeah, so traditionally, we've seen bumps, right? Solder bumps, copper pillars. This was the advent of flip chip. And we could get tens of thousands of these on a large design, right? We started at 200 something micron pitch. We moved down to 150 micron pitch. We're currently right around 100 micron pitch, give or take, for copper bumps. And that's evolved. That's the green line evolution. Around a decade ago, 2.5D integration. So you asked Paul, I think, about 2.5D integration. This is chip on interposer, which get largely connected through micro bumps. So the pitch of micro bumps is in the 50 micron range and decreasing, right? We've seen micro bumps start to shrink as yields improve, as the technology improves. We're seeing a down, I should say, an upturn in micropillar density, or a shrinking of the pitch of micropillars. And then just recently, right, as 3D is starting to really be a viable, buildable option, we get into what's called hybrid bond pads. And these are the pads that are actually used to connect chip to chip through a 3D stack. And they're really, today, they're quite large, 2 microns pitch, give or take, maybe 3 micron pitch. But they're, I don't have a slide in here. There is a great picture from AMD that showed a very custom, effectively a wire out. So they actually just took a high plane metal layer, for those that are familiar with lithography on chips, high plane metal layer, and just stuck it right between the two. And their hybrid bond pitch was very small. The point is, the pitch is radically decreasing. It's allowing us to get a lot more signal interconnect in these designs. And if I take that curve and I sort of overlay it on our decreasing scaling, you can kind of ask the question, who's lame? Moore's law is dead. Everything is now shifted towards packaging. And again, this is a marketing chart from a package engineer, so the logic guy standing in front of you looks lame, but it's true, right? So will this trend of increasing interconnect slow down? And you know the answer already. No, it's not going to slow down. It's only going to get tighter and tighter and tighter. We're already seeing R&D work on 0.4 micron pitches and beyond, out into the relatively near future. We're seeing very, very small very, very small pitches. As I mentioned, AMD, there's some other very large ones that are almost doing wire-to-wire connect, which gets you tremendously tight and super high density signaling between multiple chips in a footprint. I'm willing to explain some of this more if people have questions afterwards.
So this is the signaling. What happens with your power?
Good question. Very good question. So power can follow the same approach, but obviously, when you have such high power density, you need a lot of signals to carry your power, especially if they're these small little strands. And then you're building in redundancy in case one of those strands breaks. So there's a lot of different solutions to this. Some people are doing very fat power pillars with these little signals around, but that causes a whole bunch of noise and other issues, capacitance issues. Others are doing just massive power striping. And I think one of the most interesting aspects of this is the communication mechanisms being used. So rather than just a bunch of these signals going between chips, let's start to come up with really creative digital circuits to start serializing. So I think we're going to start seeing some of the very, very high speed serialization going between chips, which is going to come with its own baggage. How do I get such high frequencies to pass through? Can I do that between these large pillars of power to help avoid noise and mitigate or provide isolation for mitigating spurious noise, things like that. So this is the development happening right now, and there aren't any good answers. Well, I should say, there aren't any solid solutions. Everybody's got an answer, and everybody's doing it a slightly different way. And it's very architecture driven too, right? If I've separated my 3D stacks in a way that limits the amount of signaling that I need to go through those, then I still have a viable solution without needing to get ultra low pitch. But if I'm trying to take a regular design that's just out of silicon area and 3Dize it, I'm going to really struggle. And that kind of goes back to the question of, you really need to understand your package strategy before you even start logic design. It is literally gating and resetting your architectural decisions based on how you're going to package the product. Yeah.
So maybe you can help a non-chip designer here.
Sure.
If we're hitting the limits of what CPUs can do for compute, how much does signaling help us? Is it just getting more signaled into a system that's already constrained?
Yeah, the takeaway here is, to achieve the performance metrics that we need more silicon. So Moore's law doesn't scale.
This is all about connecting more pieces.
It's all about trying to get more silicon into the system.
We need more interconnects.
Exactly. And to do that, I need to connect those all. And so now I'm moving into this realm of new package, right? New chip package type of techniques, lower pitches in that connectivity, higher bandwidth, faster interfacing, et cetera. Yes. In a physical way. Like, this is not talking about the logic structures, the unique PHYs, the digital way I can do this. This is just talking about the physical aspect of it. So it's clearly drinking. There's a little marketing too, I apologize. It's clearly drinking from a fire hose. The key takeaway is it's not slowing down, and that this is actually, everybody recognizes that package is really the new hill to climb. And not only is it table stakes, but it's really the differentiator. So everybody's doing it differently. There's not a standard. There's not a one size fits all. It's architecture based. It's program based. It's system based. It's rollout based. There's a lot of customization that goes into this. And if you're familiar with chip design, or if you're in the chip design industry, that's not going away, right? We're still doing chip design. It's just how we're doing it in the way that we're aggregating it into a system package is revolutionizing. And if you ask me and many others, it is really the only way to continue to realize scaling in digital and analog technology. All right, so using AI. I always like this slide. The unsettling solution. We use the machines to build it for us, right? And clearly the question that everybody asks is, what could go wrong? And then insert picture of Terminator and the world ending and all that. But this is already happening, right? I mean, clearly. Google is using this in their TPU design. TPU is the tensor processor unit. They're in version 6. This is a very famous design that Google started back in the late 2010s, and they're using their algorithms to constantly enhance their own design. And layout engineers will see this, and probably nobody else. But this is lifted right off of Google's website. But we're a typical layout engineer might organize their memories or their complex IP and then their logic. The AI will come along and kind of figure out a better solution that the human would never think about. And even if you take it away from layout design, right? AI is thinking of solutions that we just don't think about in our biases. Was there a question?
No, I just want to point out that I think it's the January issue IEEE Spectrum magazine has an article on using AI for floor plan.
Yeah. Oh, great. I think I wonder if this. Well, this is from 2021, but I may have come across that. It did or did not? Okay. Another one is the one everybody's heard of, NVIDIA, right? Given any day the most expensive company on earth. They have very specific and common algorithms that they constantly build, just like any large hyperscaler would. And they have really tuned their layout program, their layout algorithm to recognize that. Prefix reinforcement learning is RL. To the point where they can get significantly better densities than off-the-shelf EDA tools. Now, of course, customization is almost always going to be better than something you can get off the shelf, but this is constantly training itself. And they've got it to a point where they can plug in their new algorithm, their new algorithmic layout component, and prefix RL will learn from it, slurp it up, and then give you a better density. And again, this is a couple of years old, I think, so forgive me, but these have even taken leaps and bounds since. So we're using machine learning to make these decisions, right? We're partitioning into multiple chips, being careful with bandwidth, power, and latency decisions. We're making choices in technology, trading off area and cost where we can, right? Analog and non-scaling things on older or more classic nodes, larger nodes, where we're using the newest nodes for the most complex and high performance function. And then memory hierarchies, right? Gone are sort of I shouldn't say gone, but quickly disappearing are just sort of the typical engagements with memory vendors. And now we're approaching memory vendors for customization across the board. Higher bandwidth, lower cost, extra capacity, closer to the custom function that we want in an integrated solution. So aircraft didn't stop getting faster. Aircraft stopped getting faster, but their efficiency didn't, right? And one of the takeaways is that AI is going to lead the way in improving its own physical and ecological footprint. It's the only way. We can't keep going at the rate we're going and at the scale we're going without trying to improve it along the way. And the last thing I'll leave you with. So you saw all the massive compute power that it takes to just train a simple generative AI program, or seemingly simple generative AI program. The human brain is capable of about 10 to the 18th flops, even within an order of magnitude or a couple orders of magnitude, 10 to the 18th flops. But it does it at a frequency of about 200 hertz with 20 watts of power. We have a long way to go. Any questions that I didn't answer? Yeah, go ahead. Chris.
On one of the early slides, you showed the exponential growth in cost per
I can find it.
AI.
Oh, that first one. Yes, this guy.
Does that prediction, does that prediction include all the infrastructure?
I think so. I think it has to. The nuclear plants, power plants that have to be built. I think so. That's the only way I can see it really getting to that scale. I mean, $115 million for a system to do 30 days of training is a significant cost, but it's a drop in the bucket compared to GDP. But now when I'm now when I'm opening new power plants and routing new power transmission just to provide enough capacity for it, I'm getting up into lots and lots of spend. And it's not slowing down. So it'll be interesting to look at this picture 5 years from now and see where we really ended up, right? I mean, I did make I don't remember what slide it was. I did say, the trouble with extrapolating curves, but this is clearly a disruptor. AI is clearly a disruptor in industry.
Yeah, it was
several industries.
I was at a talk from someone from NVIDIA who said that the model size is increasing by about a factor of 10 every 2 years.
It's unbelievable. To the point where they're the most expensive company on earth.
Yeah.
I mean, that alone kind of makes you shudder a little bit. Other questions? Yeah.
A question back on the NVIDIA H100. I was reading a description of it, and that's the GPU's matrix manipulation. But it says that it also has the Intel Xeon cores. What are those used for?
That's a good, so I'm not an NVIDIA engineer, so I don't know. I know that the primary function is a homegrown custom GPU function. I don't know if they use those Xeon cores for communication or interconnect. I'm not sure. These are, if you go Google these things, they're incredible looking. Like, I don't know, some of the pictures, especially in the latest investor shows that NVIDIA's done, those systems they bring out that have like 2 giant cores on them and all of the heat sink. It's just unbelievable that and the cost of those is as high as it is, and people are just buying them left and right. They cannot keep them stocked. I think it was these came out in, I think they previewed in late 2023. And NVIDIA said they were only going to be able to make 500,000 of them in the year 2024. And they were gone before they were built at, $40,000 or $50,000 a pop when they came out. So yeah, I mean, and the people buying them, the Microsoft, the Googles, the Metas of the world with deep pockets. And they're just going to get deeper, as they race to scale in AI. Yeah.
So, interesting thing that we're talking about here, sort of jump between the two of them. The start of this and what you're talking about here is time to train and resources to train, but you don't care about training, you care about inferencing, right? Because you're using the AI to do your job, and the inferencing does not require the same compute. So I'm curious, given that you're essentially an end user of AI, at least describe going forward, do you feel the NVIDIA H100 is the future, or can you just deal with better inferencing engines and not have to worry about an H100 for training an LLM?
Yeah, I don't think that this is a linear. I think there's a lot. So if I can restate your question, I think there's a lot of architectural improvement that can be done that don't necessitate linear or exponential growth in flop and compute, right? So we can certainly get better at the algorithms. That's why, I said so GPT is notoriously secretive about how they train and the resources that they use. So this 2 trillion parameters is really kind of an estimate based on GPT-3, which I think used 300 billion. And a lot of people, there's a lot of talk, and this is like Reddit threads, right? So take it for what it is. But there's a lot of discussion about how different architectural choices have actually made the number of parameters not jump that much. And instead, they've done a lot with architecture to overcome some of the computing needs. So I just made an assumption based on sort of natural scaling and performance of 4/3 to get this. But I think the answer is at every step of the design, there are more efficient architectural choices that can be made. Now, you said, I don't care about training, I care about inference. Well, I'm the hardware designer that's building the machine that ultimately needs to be used for training. You're right, training is a small portion of when the thing is actually going to be rolled out. But then we're also constantly training, right? So it's not like we train once and then we just set it aside and then GPT-4 is there in perpetuity. It's constantly training and reinforcing, and that takes a lot of compute. Yeah.
Brandon, a couple on the packaging technology again.
Sure.
The silicon interposer that you mentioned before, considered for 2.5D, just for example, do those tend to be passive interconnect only,
Good
or is it
question.
some active circuitry?
Yeah. Do I have the CoWoS pictures here? I bet I don't. So interposers and CoWoS started as passive.
Yeah.
Where was it? I don't remember. Sorry, maybe it was here. There's so many animations and everything. Yeah. So CoWoS started as like RDL interconnect.
Yeah.
Or even actually copper interconnect. I had copper interconnect, 4 layers, maybe 6, and no active devices whatsoever, all passive. And I would put an HBM memory, and I would put my logic die, and I would call it a day, and that allowed me to scale.
Yeah.
That has a reticle limit. That's the 3.3. Like I can't grow much more than 3.3x of a reticle in that technology, to the point where I need to start going to RDL, organic, which allows me to go more, but it's still kind of passive. I don't put any active stuff on RDL. But then I need to start really expanding and growing. And now I've got stuff, what do they call it? LSI, not the company LSI, but the acronym. I can't remember, logic scale integration, or somebody help me out if you know it. Where I'm actually starting to put active circuits, repowering, buffering, stuff like that. I can also put pipelining so that I can pipeline between chips now. So we're going to see more and more of that, to the point where, and I mentioned at the top, but we're now talking about interposer on interposer. So I've got, interposer with a stack, and then another stack with interposer on top of it. So the sandwich, right? The sandwich chip with backside power delivery. I have no idea how you're going to get the heat out of that thing.
And how about the package substrate itself? It's standard organic like we've always used, or is it changing based on some of this other activity?
I don't know, because I'm not a package engineer. But the shifts have been certainly away from lid. So almost everything these days is lidless.
Right. Okay.
Stiffener rings, heat sink right on top of it. So now you're going for like monoplane design. So when you're doing 3D and 3.5D, right, and you've got all these different, if you think about this, this is going to be hard to see, but you've got a chip, and then you've got like a memory stack. I've got to be able to put a heat sink on that without, sorry, I need to be able to put a cooler on that without a heat sink. But because of this stair step, I'm starting to get either very fancy designs with very tight tolerances, or I'm needing to do things in my thinning of die and that to plane things out so that I can bind them. Right, and especially when you get to 3D, then you can't build stair step chips anymore. Now everything has to be planed, and so we're thinning wafers as we go.
Okay.
Other questions? Yeah.
So what's the role of, I just want to call them like the instruction sets for the chips, but the ability for the hardware to handle, say, different types of vector mathematics versus matrix mathematics versus, just single float point operations?
Yeah. You need a logic designer. You need an architect. I'm just a lowly silicon guy. It matters. I mean, clearly. So I don't see all of these hyperscaler companies as necessarily directly competing. I think they're all doing something unique and novel. So I think NVIDIA has its own approach with its own custom traffic patterns and its own architectural solution to that. And Microsoft has a different data set. They have a different opportunity or target they're going after. And Google, right? Google is not that Microsoft isn't search, but Google is all search-based. So their pattern set looks even different. So I think all of them have different algorithms that they're targeting that aren't necessarily competing. Now, are they all trying to leverage the same solution and build? Yeah, to the extent that they can. But even that is so custom now that maybe from that architectural decision all the way through to end product is a complete custom approach just for that solution. So I didn't really answer your question, but I did the best I could as a lowly silicon design guy. Other questions? Awesome. Well, thank you very much. I appreciate you having me.